So the first and most fundamental thing that we're going to need in order to talk about how close two real numbers are, or two things are within analysis and topology, is a notion of interior point. What is it going to mean for a point to be an interior point of a set? This is going to be an important notion because it's going to let us speak of which points inside of a set have a little bit of breathing room around them and which ones do not. It's those points with a little bit of breathing room that we call the interior points, and these are going to be fundamental to our definition of what gets to be an open set. Let's take a look at how it works. So our story begins with a subset A of the real numbers. And we don't know what this subset looks like. Maybe it's kind of nasty. I'm just going to make it kind of this purple cloud of real numbers over here, as well as a point x that is inside of that subset. The question is, what do we need in order to come up with a reasonable notion of what it means for that point, that number, to have a little bit of wiggle room within that set without having to leave that set? Does it have a little bit of wiggle room around it that is entirely within that set? Those are going to be the points that we want to be called the interior points of A. So let's imagine that I'm standing on the real number line at the point x. The question is, can I reach out my arms just a little bit, even if it's just a little bit, to both sides of me and not touch anything that's outside of A? So can I reach out my arms and have my arms and hands and everything in the middle be entirely within the set A? And so this question probably depends on how long my arms are. If I reach out too far, chances are I'm going to eventually reach out outside of my set, unless my set is the entire real line, right? And so probably we might need to make our arms really, really short in order to make this happen, but as long as we can do it with some small, short, positive lengths of our arms, those are going to be the points we want to be called interior points. And so the fundamental notion that goes into this definition is the idea of what we call an epsilon neighborhood, or sometimes an epsilon ball. It's a ball of radius epsilon around the point x. And so we're going to think of epsilon as being the length of one of our arms that we're reaching out to our sides. And by convention, we're always going to reach out the same amount to our left as we do to our right, so our arms aren't asymmetric. So an epsilon neighborhood at a point x with a radius epsilon, which we're going to agree is a positive number. It's not going to make sense for us to have a ball of radius 0 or a ball with a negative radius. So epsilon is going to be our positive length of one of our arms. And the epsilon neighborhood is nothing more than that set, which we're going to denote by b sub epsilon of x, the epsilon ball at x, which consists of all of the real numbers which are at a distance of less than epsilon away from us at x. So if we're talking about the real numbers in the real number line, that's nothing more than the open interval from x minus epsilon to x plus epsilon. Right? The left endpoint over here, the right endpoint over there, and everything in between. So that open interval is what we call the epsilon ball centered at the real number x. So we want to call x an interior point of A if it's true that if my arms are short enough, I can reach out to both sides of myself and not touch anything that's outside of the set A. So all of me, my arms, my hands, everything that I can touch is all elements of A. That's what it's going to mean to be an interior point. So to make this mathematical, we'll just say that what we need here is we need everything within my arm's reach, in other words, the epsilon neighborhood at x, to be a subset of A. That's the power of this definition. This definition just says I am an interior point if I have an epsilon ball, even if it's a really, really small one, as long as there's some positive radius epsilon ball centered at me, which entirely resides, is a subset of A. And all we need is one example. We don't need this to be true for a bunch of different arm lengths or radii or whatever. We just need a single value of epsilon for which the epsilon ball is a subset of A. And so we get the existential quantifier in this definition. X is an interior point of the set A. If there exists a positive epsilon, however small it needs to be, as long as it's positive, such that the epsilon ball centered at x is entirely a subset of the set A. It gives me an epsilon ball's worth of wiggle room for which I do not have to leave the set A. So let's do an example. If I take the set of all points inside of A which get to be interior points, all of them that satisfy this definition, we get a set called the interior of A. So let's see if we can determine what are all of the interior points, in other words, what is the interior as a set, of the set A, which is the interval from -2 to 4, inclusive of -2, union together with the singleton point at 6. Let's sketch it out. So I have this, everything in between -2 and 4 shaded in. -2 solid circle because we're including -2. 4 will be an open circle because we're not including 4, and then I'll put a little dot up here at 6. So this is what my set A kind of looks like. Let's figure out which points of A are interior points. And to do this, I'm just going to kind of imagine standing at various places throughout this set, and then ask the question, can I reach out my arms without leaving the set, even if my arms have to be really, really tiny to do so? So where can I stand and stretch? That's the question that we're trying to answer if the question is, what's the interior of this set? What's the set of all interior points that we can find? Well, the first place that I want to stand is right here in kind of the smack in the middle, in between -2 and 4, but not at one of those endpoints, just somewhere in between. Is it possible for me to stretch out my arms if I'm standing, for example, at, I don't know, -1, or -2, or +π, right? Any of those numbers that are in between -2 and 4, yes, I can stretch out my arms, even if it has to be a really, really small amount, even if I'm standing at 3.9999, right? There is some small little tiny radius that I can stretch out, and my epsilon neighborhood be entirely contained within A. So if x is any point between -2 and +4, exclusive of the endpoints, then x is going to be one of the interior points of A. Those are going to be good. We want to include those points in our answer. So what haven't we covered? Well, what about the number 4? Can I stand at 4 and stretch out my arms? Well, the problem is, at 4, there's nowhere for me to stand in the set A. And this is a really crucial point about interior points. Interior points of a set have to, a priori, be elements of that set to begin with. So if I'm not already in A, I don't get to be an interior point of A. That's the definition of what interior means. Right? We have to first be in A and then be able to stretch our arms. 4, because it's not in A to begin with, cannot be one of A's interior points. So 4 doesn't work, for sure. We have to bypass that one. What about 6? Can I stand at 6? Because 6 is an element of A. Can I stretch out my arms at 6 without leaving the set? And the answer this time is no. No matter how short my arms are, as soon as I reach outside of 6, I'm going to be touching elements, numbers like 5.999, for example, which are not elements of the set A. So no matter how short my arms are, if I'm standing at 6, I'm going to touch elements outside of A when I reach out my arms. So the number 6, even though it's an element of A, does not get to be an interior point of A. And as you might imagine, the same thing is true about -2. When I stand at -2 and I reach out my arms to both sides, there's one direction that I can reach. If I reach out to my left, your right on the screen here, then all of those points that I touch, if my arm is short enough, are going to be elements of A. But when I reach out to my right, or your left, right, when I reach out toward the negative side of the number line, I'm definitely, no matter how short my arms are, going to be touching points which lie outside of A. And so -2 also does not get to be an interior point of A. It's a point of A, but it's not one at which I can reach out to both sides, so that's a key part of the definition of epsilon neighborhood. I can't reach out to both sides, no matter how short my arms are, without touching something that's outside of A. So -2 does not get to be a part of the interior. Taking stock, the interior of A is going to then consist only of those real numbers between -2 and 4, but it's not going to include -2 because of this arm that reaches outside of the set. It's not going to include 4 because 4 wasn't in the set in the first place. And it's not going to include 6 because, same problem, no matter how short my arms are at 6, I can't reach out without touching something that's outside of the set A. So the interior consists just of the open interval from -2 to 4. So that's the idea behind interior points. We build our entire notion of what we call the metric topology of the real number line around this notion of interior points. These little tiny epsilon neighborhoods, they might be tiny, they might be large, but as long as they exist around a point in my set and they don't flop outside of that set somehow, then those are the points that we call interior points. And the interior points are going to be fundamental to our definition and notions of openness. Sets that kind of don't have a clearly defined boundary that they contain, but they're sort of, we can approach the horizon of the edge of our set but not actually leave it, right? Those open sets are defined using interior points, and that's the next thing that we're going to take a look at in the next video clip.